All right, I'm going to do a video for section 11.1. All right, so this is kind of a long section. It deals with basic probability, but it also gets into the idea of odds. All right, so first off, not everything is something, not every situation is one where using probability would make sense. For instance, if we knew tomatoes are $1.39 a pound and we were asked how much will 5 pounds of tomatoes cost, that's not really a probability situation because the cost is set and we're buying a set amount, and so we could just determine it by doing 5 times $1.39 and working that out, okay? And let's see, let me go ahead and calculate that. So 5 times 139 means those tomatoes would cost us $6.95, okay? So it's determined. It's not up to, there's not like a likelihood of it being that much. That's what it's going to be if the tomatoes are $1.39 a pound. Okay, so that kind of phenomenon, that kind of situation is a deterministic situation, okay? And then I want you to contrast that with the idea of a random phenomenon. Phenomena just is a plural for that. So random phenomena fluctuate in such a way that you can't predict exactly, okay? So, but even though we might not know for certain what the result would be, we can have a sense of how likely it would be or what its probability would be, okay? So probability is like the likelihood of something happening. Okay, so when you are looking at a observation or a measurement of something random, that's called an experiment. Okay, so that's like rolling a die or tossing a coin would be your experiment, and then the possible results of that experiment would be the outcomes. So here what we're doing is, back in chapter 10, we had experiments. We just didn't necessarily call them that. And then we had outcomes, but we just called them possible results. And if you look at the set of all possible outcomes, that would be the sample space. Okay? So that was like back in chapter 10 when we were listing possible results. Okay? So think about rolling a normal 6-sided die that you use for like Monopoly, okay? The experiment would be rolling the die, okay? The outcomes would be a 1, a 2, a 3, and so on, up to 6. And then all of those, right, would be the sample space for that experiment, okay? Now, we're usually interested in some particular collection of those outcomes. So that would be like, maybe we just want, what's the probability of getting an even number? Or what's the probability of getting a number less than 3? So any subset of the sample space. So any, what they call event, any subset of the sample space, like getting a number less than 3, that would be just 1 or 2. So that subset, that 1 and 2, getting a 1 or a 2, that would be an event. The experiment is rolling the die. The event is what we're looking for, what we're interested in. So we might be interested in what's the chance of getting a number or probability of getting a number less than 3, which would be just 1 or 2. That would be called an event. Okay. And then the outcomes that belong to the event, sometimes we say fit the event, okay, those are going to be what they call the favorable outcomes, the ones that you would want to count, okay? So they're the successes or the favorable outcomes. So again, think about the probability of rolling the die and getting a number less than 3. Then if we're doing that, getting a number less than 3, the favorable outcomes would be the 1 or the 2. And then the others, which would be later, we'll talk about them being unfavorable, would be 3, 4, 5, and 6. Okay. All right, now, the probability of an event happening, like the probability of getting a number less than 3 when rolling a die, the probability of an event is a numerical measure of the event's likelihood. Now, sometimes we'll be able to determine it theoretically, which is like mathematically. But sometimes it's not possible to do that, but we can do it experimentally, which is sometimes called empirically. Okay. So back to just the idea of the theoretical probability, back to the event of getting a number less than 3. See how there's 2 outcomes that would be less than 3, and there's 6 possible outcomes? So the theoretical probability of rolling a die and getting a number less than 3 would be 1/3. Okay? Now we'll talk more about the experimental probability in a little bit, but that would be if there's no set, you can't know for certain. Like one good example is when you're, say, tossing a cup, it might land on the bottom, it might land on the top, or it might land on the side. And there's no set mathematical probability that you can determine for the cup landing on its side. But you could perform that experiment of tossing a cup a bunch of times and get a sense of what's the likelihood that that would happen. That would be empirical probability. Okay. All right, so the theoretical probability formula is what we're looking at here. So if we have some event that could happen when an experiment like rolling a die is performed, so the event could be, could be getting a number less than 3, okay? The experiment was rolling a die. Oops, wrote it on the wrong one. I meant for that on the theoretical one. Let me go up here. Okay, so outcomes in a sample space are equally likely. So let's think about rolling a die. The sample space for rolling a die would be 1, 2, 3, 4, 5, or 6. The event might be something like getting a number less than 3, okay? And so that would be getting a 1 or a 2. So then the theoretical probability of getting a number less than 3 when you roll a die could be determined by thinking about how many of the outcomes are less than 3. There's 2 of them, and how many outcomes are there in the sample space, like how many possibilities in the sample space. 6, and then you reduce it, okay? All right, now, empirical probability formula is similar to that. It's just like if we were tossing the cup, so we've got a cup maybe that looks something like that, and we're just going to toss it a bunch of times and see what happens. Then it might land bottom up some of the time. It might land top down some of the time. And then some of the time it would land on its side. And what we could do is just perform the experiment a bunch of times to get a sense of what the probability for the cup landing on its side might be. Okay, so the event in that case, that example, might be the cup landing on its side. Okay, the experiment is tossing a cup, like a red Solo cup. Okay, then we could determine the probability of that happening by just taking how many times it landed on its side divided by how many times I tossed the cup. So the number of times I tossed the cup not cop. Okay, and then number of times the event occurred. The event in this case might be landing on its side. So we would just count up how often that happened and divide that by how often I tossed the cup. All right, now probabilities can be written as fractions, decimals, and percents. I mean, those are really just 3 different ways to express the same thing. If the probabilities are written as fractions or decimals, your probability is going to be between 0, if something can't happen, and 1, if the event has to happen. All right, now sometimes what we did in chapter 10 with the combinations and the permutations, sometimes those could be used, or the fundamental counting principle could be used to figure out the number of outcomes in the sample space, or the number of times some event would happen. You just do whatever makes sense in that context. So we'll see several examples of that later. Okay? All right, so let's go ahead and think about some of these questions. Let me see if I asked. All right, let me go ahead and give you an example of the impossible event, because I don't think I asked it later. Okay, so let me go back to this where I said the probabilities would range from 0 to 1. For an impossible event, that might be rolling a die and getting a number greater than 6, okay? So the probability of getting a number greater than 6, well, the only possibilities are 1, 2, 3, 4, 5, or 6, so it's not possible. Then that would be a probability that would be, there's none out of the 6 possible outcomes, so that would be 0. But if I were rolling a die and the probability, I wanted to know the probability of getting a number that was less than 7, okay, I'm always going to get a number less than 7, so that would be 6 out of 6, which would equal 1. Okay. All right, now let's go just work in some basic probability problems. You're going to find that these are pretty intuitive, okay, initially. All right, so here we've got the spinner that you see on the right with the numbers 1, 2, and 3. It's going to be spun twice to determine a 2-digit number, and we need to determine the sample space. So we need the actual sample space. They didn't just say the number of elements in the sample space. So one way to do it would be to think about a tree. Okay, so that's the first spin to determine maybe the tens place, and then I'm going to spin it again. Right, so I have an option of those. And they didn't say anything about not being able to use the number more than once, and there's nothing that would prevent that from happening, you know, with the spinner itself. So then if they want the actual sample space, you would go on and you would list them. You're creating 2-digit numbers, 11, 12, 13, 21, 22, 23, 31, 32, 33. Now you wouldn't actually have to draw the tree. This is the list I would want, and you'd need to be able to find it somehow. You know, some of you like the product table idea. You could have done that to reason it out and seen the 1, 1, 1, 2, 1, 3, and then the 2, 1, 2, 2, 2, 3, and then the 3, 1, 3, 2, 3, 3. Okay? And then that part of it gives you your sample space. So we want to actually see those 9 numbers. All right, now, if you actually can do that and see the sample space, then these probability questions are really just a matter of counting up the right stuff. So the experiment is spinning the spinner twice. Okay, the event we're looking at is the probability of getting an odd number. So we're going to look at our sample space, this list of possibilities, and we're going to see which ones are odd. So they have to end in an odd number. So those, the 11, 21, 31, the 13, 23, and 33. So there's 6 of the outcomes in the sample space that fit, that are favorable to the event of getting an odd number, and there were 9 outcomes in the sample space. And then simplify that, and your calculator can simplify fractions for you if you need it to. All right, the next one wanted the probability of getting a number with repeated digits. So you can see that would be along this diagonal here, these three. Okay, so that's 3 outcomes out of 9, which you would simplify and get 1/3. And then if we wanted a number greater than 30, that would also be 3, because there's just these 3 numbers, 31, 32, and 33, that are favorable to the event of getting a number greater than 30, and then there are 9 in the sample space. Okay. All right, and that's really all there is to it. All right, let's try another one. This one says, what's the probability of landing on these various colors? Yellow, blue, red, or blue. Okay. So I can't print in color, so I put the letters R, Y, or B on things. And all of the spaces are equally sized, so they're equally likely. But do you notice that 3 of them are red, 2 of them are yellow, and 1 of them is blue? So that means red would be the most likely, wouldn't it? So if we wanted the probability of landing on yellow, we can see that 2 of those sectors are yellow, and there's 6 possible sectors, so you have a 1 out of 3 chance. The probability would be 1/3 for that. With blue, you just got a 1 out of 6 chance of landing on blue. Probability would be 1/6. And for red, there's 3 red ones with 6 out of the 6 sectors, and when you simplify that, you have a 50-50 chance. The probability would be 1/2 that you would land on red. Now, what if I threw in the word or, with or being like it was in both logic and sets, where you could be just red, just blue, or both. In this context, you really can't be both. So you would think, okay, there's 3 red ones and 1 blue one, right? So there's 3 red ones and 1 blue one, and you would divide by 6 still. So there's 4 possibilities. 4 of the sectors would be red or blue out of the 6. So the probability would be 2/3. All right. Now, here's one that's really definitely empirical probability. And when you're looking at this one, this reminds me of my father-in-law. He was a plant breeder. And so they actually would take plots of land and plant seeds and then see how many of them actually came up. And then that would give you that information about how likely the seed would be to germinate. And so, of course, you want to you want it to be where as many as possible are actually going to germinate. So you do different experiments, you look at different fertilizers, you look at different, maybe breed different types of seeds that would have maybe turn out to have a better outcome. Okay? So with this particular one, 200 seeds were planted and 175 of them germinated. That just means they sprouted. Find the empirical probability that any seed of this type will germinate. So there were 175 that germinated out of the 200 that were planted. Okay? And then you would simplify that. If you divided top and bottom by 25, the top would be 7, the bottom would be 8. So your simplest form would be 7/8. Now you sometimes are asked to put it as a decimal. So you can change from fractions to decimals. Most calculators will have a key that looks like that. Some of them have this key that has an S to D. And on some of them, you just hit your equal sign multiple times, and it will just change between different forms of a number. All right, now here's that plastic cup situation I alluded to earlier. So there's no theoretical probability that would tell us, enable us to figure out the answer. And that's because landing on the bottom versus the top versus the side is not set like it is for like rolling a die, where it's equally likely to get any one of those 6 outcomes. So we've done an experiment, tossing a cup 50 times. So it landed on its side 44 times, on its top 5 times, and on its bottom just once. We want the probability that it will land on its top. So it landed on the top 5 times out of 50, and then if we simplify that, the probability of landing on its top, we would say, is 1/10. 1 out of 10. All right, now that's basic probability. Now I'm going to do a different video in a moment for some other components of this notes page.